Howdy AP PreCal, it's Miss Kosh. We are looking at binomial expansion today. This is something that has been taught in PreCal and hasn't been taught in PreCal. It's not currently Texas Essential Knowledge and Skills for Pre-Calculus, so I haven't taught it in Pre-Calculus in a little while, but I have been teaching it in IB. So yes, this is something I really enjoy, and actually HLIB does some crazy stuff with this that, well, I can't really get into, but go find my videos if you're intrigued. Okay, so to begin with, I'm kind of generating, this first page, we kind of generate the idea of how to do it, and then the second page we practice. Okay, so the ultimate goal, and I think, to be honest with you, I think AP PreCal is going to stick to this kind of thing. This is a little bit of an extension that I love to do with IB. So we'll see how far we make it in this video and see if I need to make a second video. Okay, getting started. Anything to the 0 power is 1. Okay, and then if I have this one, if I have a plus b and I just have it to the first power, it's just equal to a plus b. And then when I have this one we know a squared plus 2ab plus b squared. And now what I need to do on this one is a plus b to the third is a plus b to the second times another a plus b. This video would get really long if I showed you how to FOIL that out. Basically, pulling the scratch paper from the last video, if I have a squared plus 2ab plus b squared and I want to multiply it times a plus b, that would be a plus b cubed. I can multiply all the way through, combine out my like terms. Will you trust me and just assume that I know that this is going to be a cubed plus 3a squared b plus 3ab squared. I should have told you pause the video and go try it yourself. But if you don't believe me, go try it yourself. Then now pause the video, don't pause it yet. Take this one. To get to the next a plus b to the fourth is going to be a plus b to the third times another a plus b. So go try this method, except now we're taking, instead of this, we now have this a cubed plus 3a squared b plus 3ab squared plus b cubed. When I do, I end up getting a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Now in class I might have y'all do it on the board and kind of prove that this is true and make you do it at your desk, but I didn't want to spend time on the video. Now here's what's happening with this. If I put ones everywhere where I didn't have a coefficient, we have this pattern of numbers that's going to be really cool. Let me lead you to, so here's the pattern, and it's called what we call Pascal's triangle. So the idea is that our outside numbers are always ones, and then we add these two together to get this middle term. So if I'm going, so it's always ones on the outside, and then I have a 1 plus 1 gives you this 2, 1 plus 2 gives you 3, 2 plus 1 gives you 3. So this row of Pascal's triangle is 1, 3, 3, 1. And then I have 1, and then I add these together, this is 4. Add these together, this is 6. Add those together, that's 4. And we write down another 1. Again, 1, we add these, this is 5, this is 10, this is 10, this is 5, this is 1. If I were to keep going, what I would get is 1, 6, 15, 20, 15, 6, and 1. And there's a lot of cool things about this. I don't know that I have enough time in this video to show you everything, but it's super cool. Notice on here that so say this row right here, 1, 4, 6, 4, 1, is 1, 4, 6, 4, 1. Oh, you couldn't see me. Okay, let me try that again. 1, 4, 6, 4, 1 matches 1, 4, 6, 4, 1. So that gives you, Pascal's triangle gives you the coefficients in a binomial expansion. One other thing about Pascal's triangle is if we call this the 0 row, and then we call this the first row, and we call this the second row, and call this the third row, it's technically the fourth row, but if you call it the third, if you call it the number that shows up, then it matches the exponent up here. Okay, so think about it. When I got just 1, I got just 1 by raising it to the 0 power. Okay, there's more stuff that's super cool. So what I like to do is I like to use my name. And how many ways, if I have the letters K-O-S-H, how many ways can I pick none of them? Well, only one way. I got none of them. I'm done. There's nothing to write down. I've written down nothing. We're done. How many ways can I pick one letter? Well, I could pick K, or I could pick O, or I could pick S, or I could pick H. So I have 4 ways that I can pick just one letter. Okay, what about 2 letters? Well, I could pick K and O. I could pick K and S. I could pick K and H. I could pick, let's start with O. I could pick O and S. I could pick O and H. Or I could pick, I've done all the O's, okay, or I could pick S and H. Now this is like, these are what we call a combination where it doesn't matter what order we pick them in. It's more like we're selecting winners to go on a cruise versus picking first, second, third place at a horse race. Okay, we will talk more about this or just go Google combinations and permutations. These are combinations, we're not talking about permutations. But notice here we have 6 ways to do that. How many ways can I pick 3 letters? Well, I could leave off the H, I could leave off the S, I could leave off the O, or I could leave off the K. So really this is how many ways can I not pick a letter? That's the same. So there are 4 ways here. Oh, another thing while I'm thinking about it, do you see the symmetry in Pascal's triangle? Kind of in this middle, like I could get to a middle point and fold it and they match up exactly, which is another thing that's pretty cool. How many ways can I pick 4 letters? I can pick all 4 of them just one way. And so there's one way I can pick that. So what these are, these combinations, notice this 1, 4, 6, 4, 1, that showed up here, 1, 4, 6, 4, 1, that showed up here, 1, 4, 6, 4, 1. So what's happening here is that we can write any row of Pascal's triangle using combinations. So for example, this 4 row, well, okay, so what conclusions can I draw from this page? 1, we can use Pascal's triangle to expand binomials. That's one thing. The second thing is that every element of Pascal's triangle can be described with a combination. So one way to write the formula is NCR, and that's kind of what it looks like in your calculator. My IB kids will write it like this, where it's kind of a matrix, kind of a vector, kind of a, I don't know, there's no line, but it's the n value over r. And the formula is n factorial over n minus r factorial. And so if I want to do, let's see if we can get this answer. This is saying 4 choose 2, or you could write it this way, 4 choose 2. When we do that, this would be equal to 4 factorial over 4 minus 2 factorial, 2 factorial. Now, if you're thinking, Miss Kosh, why are you using exclamation points? We've never seen this in our life. A factorial is where you take an integer, well, and for PreCal's purposes, we take an integer and we're multiplying by every subsequent smaller integer until we get to 1. So this would be like saying 4 times 3 times 2 times 1 divided by, this is now 2 factorial, 2 times 1, this is 2 factorial times 2 times 1. Okay, and so then this 2 times 2 is 4 and that's gone, so this is going to be equal to 6. Which is exactly what we expected from over here, which is super cool. If I were to write out, say I want to write this 5th row as combinations, I could say 5 choose 0, because anything choose, and then it's 5 choose 1, it's 5 choose 2, it's 5 choose 3, it's 5 choose 4, and the last one is 5 choose 5. The cool thing, though, is that there's symmetry. So these match, and those match. Just like up here, these match, and those match. Let's do one. It's about time to stop this video and send you to another one. But let's try one of these things and see if it matches what we expect. If I'm going to say 5 choose 2 should equal 10. Okay, do you see how that corresponds? And it should be equivalent to 5 choose 3. So let's talk about those two just to make sure we understand. So 5 choose 2, we could also write that as 5 choose 2, which is 5 factorial over 5 minus 2 factorial, 2 factorial. 5 minus 2 is 3. So I have 5 times 4 times 3 factorial over 3 factorial times 2 times 1. And there's a reason I wrote it out like that. This is 3 times 2 times 1, which will cancel with 3 times 2 times 1 right here. So if I have this in the numerator and that in the denominator, they're gone. And now I can say, okay, 2 goes into 4 2 times. I have 5 times 2, and that's equal to 10. Oh, should I grab, do I have a calculator? I do have a calculator. Dun, 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 dun. Okay, so if I exit out wherever I am, when I come in my calculator, I can go, oh, my brain just stopped. Option, come over to probability, and here is factorial, and here is NCR. So what did I just say? I said 5, choose 2. which you notice if I do 5, choose 3, they're equivalent. And the reason that is because when I do 5 factorial over 5 minus 3 factorial, this cleans up to be equivalent to that one. Do you see how this becomes 2, which was here? This is 3, which was here? Anyway, they're the same, and it's just super cool. Okay, so we have started the idea of binomial expansion, but we haven't had any problems. So go find my next video because it's going to be super cool.